Okay, it's 2:02. So I think we'll shift the focus to science. So thank you everybody for coming to the Essex seminar. Quickly before I introduce Professor Cziczo, just wanted to give a notice that this seminar is recorded and will be posted on our YouTube channel before the end of the week. So now I'll go ahead and transition to Lars Peter, our Essex director, to introduce our speaker today.
Thanks, Cassie, and welcome everybody to today's Essex seminar, and especially welcome to Dan Cziczo, who has agreed to speak to us. Dan is a professor in the Department of Earth, Atmospheric, and Planetary Sciences and the School of Aeronautics and Astronautics. That's quite a mouthful. At Purdue. He's an atmospheric scientist, and he is focusing mostly on what floats around in the atmosphere rather than the composition of the atmosphere itself. So particulate matter and how that interacts with clouds and with water vapor, and what that means for the atmosphere and the atmospheric chemistry in general. And today he's going to talk to us about what is in the interface between the troposphere and the stratosphere, upper troposphere, lower stratospheric aerosol. And I was working on lower stratospheric stuff many decades ago, and my impression was that other than a few scattered polar stratospheric clouds, there wasn't much up there. But there is something, and we know that convection puts some stuff up there, and that's part of what Dan is going to be talking about. What I realized from reading the abstract is that there's also stuff that comes down from above, and that I hadn't really thought much about. So we look forward to hearing what you have to tell us about that, Dan. Over to you.
Well, thank you so much for that introduction, and it couldn't have been more perfect because that is exactly what I wanted to talk about today. And I've used the extra word here that you didn't see in the abstract, which is unexpected complexity. And so we'll talk a little bit about this interesting interplay of what's coming down from above and what's coming up from below. I did want to start by saying thank you to John. I know that he couldn't be here, but when he first reached out about the chance to do this seminar, I was incredibly excited. He also sent a few of your past seminars, and it was a real list of amazing folks. And so I'm really happy to be counted among them. So thank you very much for the invitation. And without further ado, I'd like to go ahead and just jump in to what we're going to talk about today, which is this interesting regime of our atmosphere, this interesting region of our atmosphere between the upper troposphere and the lower stratosphere. And there's really sort of 6 things that I wanted to go over. The first is an introduction, just to remind us why we need to study this region. I want to talk a little bit about methods. So I know this is an interdisciplinary audience, as the title of your institute implies. And so I did want to mention a little bit about the methods. And so if there's any engineers in the group, I hope they enjoy this part. 2 kind of case studies, what goes up, and then the summer of 2023. I hope these will make sense as we get to them. They're kind of 2 recent papers that came out of our group. And then with the last 2 things, I'll start to close up. Just some ideas on future work, what I think we're going to need to be doing as a community in the coming years, and then just some final closing thoughts for what we're going through. So first, by way of an introduction, Lars Peters, you couldn't have set this up any better, but I always like to start with this slide, which is from a study guide for advanced placement classes. So think high school seniors in environmental sciences and how they view the atmosphere. And so it's a very cartoony diagram, but I love it in the sense that it really says a lot about our atmosphere. You know, it lays out the layers of the atmosphere, the temperature, the altitude ranges that they're found at. You can look at the troposphere. You see aircraft moving around clouds. There's a lot going on. You look a bit higher up. We're going to talk about meteors in a bit, ablating, burning up in the mesosphere, and even spacecraft higher than that we're going to talk about as well. But then you zoom in on the stratosphere, and as was alluded to when we got going, there is really no feature here whatsoever. It's almost like nothing's going on. You see these couple of measurement balloons passing through, but the color's the same. There's no clouds. There's really nothing going on. And this is really our historic thought about the stratosphere, that there was really very little taking place in this region of the atmosphere. And I think this audience knows that that's not true, but we're going to really try to explore some of these points. So right off the bat, one of the things that I want to talk about today is going to be clouds and the effect that they have on the atmosphere. And just as a reminder, there are actually clouds in the stratosphere. So if you think of that sort of tropopause stratospheric region, at the tropopause, we often have cirrus clouds completely glaciated ice clouds. And these are very important for our climate. They're one of the very few cloud types that can trap more heat than they reflect radiation back into space, so they can warm. But then the stratosphere itself actually has cloud types, and these are the famous polar stratospheric clouds. And so those aren't represented on that very cartoony figure, but they are very important. And namely, I think the reason that most of us think about polar stratospheric clouds is because of ozone depletion. So that's another feature of our stratosphere, which is that our ozone layer, by and large, is in the stratosphere, blocking UV radiation. And we can destroy that ozone using different types of chemistry, atmospheric chemistry that goes on heterogeneously. Heterogeneously meaning on the surface of particles, or even more effectively, on the surface of polar stratospheric clouds. And this was something that was really understood back in the 1980s, but it really points to our current need to continue to understand the particulate matter in the stratosphere, as well as the clouds that might be formed there. So when I say particulate matter, I don't want to lump this all together and just think of it as a bulk amount of material in the atmosphere. What I really want to do is highlight in this introduction how the material can be very heterogeneous. And by that, I mean sort of just a myriad of different particle types. And so this is just another introductory slide, this one from the Pacific Northwest National Lab, sort of pointing to where particles in our atmosphere come from. On the left-hand side, you can see condensable gases that are put into the atmosphere, condensable in the sense that they can then come together and form new particles in our atmosphere, things like sulfate, sulfuric acid, nitrates, organics coming together and forming new particles. We can also think of primary particles, meaning particles that are put there directly from the surface, this being things like mineral dust, soot from anthropogenic sources, biomass burning, which we'll talk more about as we get into it, or sea salt. And so what you can see in this slide is that, we're putting all of this material into the atmosphere. It's not only interacting with the gases around it, but with each other. It can coagulate at the same time. And then what you'll see on the right-hand side is this idea of activation and resuspension. And so what's being alluded to here is that these particles are important because they actually act as the sites on which clouds form. So they can be condensation nuclei, they can acquire liquid water and form liquid water droplets, or they can be ice nucleating particles, and they can form ice crystals, the crystals that form those cirrus clouds and those polar stratospheric clouds that I mentioned before. And so one way to kind of motivate why we need to study particulate matter and why we need a really exquisite amount of detail on it comes from this really nice paper from Nicole Reamer's group a few years ago now. And what Nicole pointed out in a very simple thought experiment was that depending on how you think about these particles, you can get very different clouds represented by essentially the same material. And so what do I mean by that? So in Nicole's thought experiment, she took just two components. So you could sort of think of this as being ammonium sulfate and an organic. And these particles are all 50-50 mixes of those two components, but the mixes themselves are different. On the far left-hand side, this is mixed homogeneously. Everything is exactly the same. Every particle is 50-50. The middle one is completely what we would call externally mixed. 50% of the particles have one thing, 50% another. And then Nicole used what she called a real world mixture, different combinations within particles, external and internal mixtures, and then different ways of mixing the particles themselves. She applied very common hygroscopic parameters to both or all three of these sets of data. And what she showed was that you get three very different clouds formed on exactly the same bulk material if you made different assumptions about how they were mixed. So in the easiest case where everything's mixed, everything activates and forms a cloud, you get 6 particles out of 6 forming a cloud. On the other two cases, the external mixture, you get about half of the particles. The hygroscopic material nucleates, the hydrophobic material does not. And then you get a cloud on 4 out of 6 particles. So yet a third different answer on the real world mixture. And so what this really highlights is that you not only need to know what's there in a bulk sense, but you really have to know how it's separated and how it exists in each particle, pointing to the level of complexity that we really need to understand about these particles to sort of get the answer right in the atmosphere. And I hate to say it, but it gets even worse than that when you start considering ice nucleation. So what Nicole was doing was thinking about droplet nucleation or condensation. Folks like Paul DeMott have thought about how much material nucleates ice in the atmosphere, and instead of being sort of 6 out of 6 or 4 out of 6, the answer is like 1 in a million particles are effective ice nucleating particles in the atmosphere. And so you can see that the level of detail is not even just 50% understanding that much material. It's really that we need resolution that's going to take us down to the 1 in a million level. And so that's what we're going to spend pretty much the next section talking about. I'll just do a quick wrap up of the introduction. I'll try to do sort of a little Cliff Notes version of each thing. But the take home message from the first few minutes really is this idea that the upper troposphere and lower stratosphere, and especially the particles in this region, are an understudied area of the planet, but they are critically important to our atmospheric chemistry and to our climate. Okay, so deep breath. The next section is the one that I hope appeals to hopefully some of the engineers in the audience, and that's how do we do this? So I've already sort of laid out the task, which is to be able to understand something about particles really on the 1 in a million level. And that sounds like quite a challenge. So how are we going to do this? Okay, so at this point, you're probably thinking, why did we invite this guy out to speak? Because he's put something up about Halley's Comet. So let me explain for a minute, and hopefully some of the science history buffs out there will enjoy this. What I just proposed, that we need to understand particles at a single particle level, is not new. That was really something that was discussed in our community dating back to the 1960s. There were even attempts to do it in the 1970s. Places like Caltech, there were groups that were trying to do this, but the technology had not caught up with doing this yet. They built instruments like what we have now, but they took up entire rooms, entire laboratory spaces. And of course, that was not something that you could easily take out into the field. It wasn't until the 1980s that we actually had a chance to start doing this, and it was really thanks to Halley's Comet. So when Halley's Comet passed by in 1986, there was a fleet. It was sometimes called a constellation of spacecraft that were sent after it. A couple of them came from the former Soviet Union, Vega 1 and Vega 2. And one of those Vegas had on it what was called a particle mass spectrometer, or a dust mass spectrometer. And it came from a German group, and it was quite interesting what they decided to do. So they were going to bring in the cometary dust particles. They went through something that was called impaction ionization, where that cometary dust particle came in and struck a target really hard and basically liberated ions from that grain, that cometary dust grain. And for the younger folks in the crowd, this is how papers were written back in the 1980s. You didn't have nice electronic animations. You actually drew these things out by hand. And so these are the ions coming off this theoretical particle. And they ended up getting this beautiful mass spectrum for the particles. Beautiful in the sense that this is essentially the first information they had on the composition of comets. This is 43 distinct grains from Halley's Comet tail that were all added together to get an ion number versus a mass to charge, essentially a chemical fingerprint. What's really interesting about this is that by having to shrink the technology down to get it on a spacecraft, taking it essentially from a room-sized instrument to a spacecraft-sized instrument, this opened up the field for everybody else. So this technology was taken back, this essentially miniaturized technology was taken back. And by the early 1990s, folks had adapted that equipment to be able to make these single particle instruments much more portable. I'll show some specifics on this in just a moment, but this is the first instrument, the first single particle instrument. It was called Particle Analysis by Laser Mass Spectrometry, PALMS. It was from Dan Murphy's group at NOAA, and they were able to put this for the first time on a stratospheric aircraft. So this is a WB-57, and they got the first measurements through the depth of the troposphere and into the stratosphere in 1988. So if anybody's interested, this paper, which is now, I guess, about a quarter of a century, a little bit over a quarter of a century old, was really a groundbreaking study. What Dan was able to do was essentially say, what is the chemical fingerprint of these particles that were in the upper troposphere and lower stratosphere? So these are single particle mass spectra. I hope you'll agree they're a little bit better quality than what was done for Halley's Comet. And Dan was able to show, for example, in the middle spectrum on the left here, the ubiquitous sulfate aerosol, sulfuric acid and water aerosol that was found in the stratosphere. But Dan found a lot of other stuff that was in the stratosphere as well. And up till this point, people really thought of it as being almost exclusively sulfuric acid and water. Dan was able to show some really interesting results. And so on the y-axis here is potential temperature. This is a surrogate essentially for altitude. You can see where typical tropopauses exist in the north and in the south here. And what Dan did was he basically traced out the sulfate ions versus the organic ions. And so what he's showing here is that as you move from the troposphere into the stratosphere, much like we were thinking about before, that aerosol becomes much more sulfate rich, almost a pure sulfuric acid and water aerosol, with a couple exceptions, which I'll talk about in a few moments. Whereas if you go from top down and move into the troposphere, you start to see a lot more organics. And these are organics from things like biomass burning, as well as those organics that we showed earlier in that cartoony slide coming off of plants, as well as anthropogenic activities at the surface in the troposphere. What Dan also pointed out is that although most of this can be encompassed in the color red here, which is sort of a heat map of things that you find in the atmosphere, he was pointing out too that if you're willing to go to small enough abundance, low enough abundance, that you can find just about anything, maybe with the exception of the noble gases on the far right on this periodic table, in the atmosphere and really even in the stratosphere. So again, it's not that nothing is there, it's just very rare at that point. And so we'll talk a little bit more about that as we go through as well. Okay. So that's the history lesson. That's where we were in the late 1990s. So what's happened more recently and why am I here today? It wouldn't be a great talk if I was just talking about data acquired in 1998. So NASA gave us the opportunity a few years ago to essentially rebuild the PALMS instrument. So this is PALMS NG, where the NG is next generation. And so I wanted to show this because this is an interesting instrument in that it was constructed completely electronically before we cut any metal for the instrument. So unlike back in the 1990s where things were drawn out in paper, very early versions of CAD software, and then you built them and found out if it fit and maybe changed some parts around, we were able to adapt this and then in sort of three-dimensional SolidWorks, figure out was this going to fit in the different aircraft that we wanted to put it on. And so we were able to do all of this. This is the thought diagram of the instrument before we even did anything with it. So I've talked a lot about these instruments. I did want to show a quick animation of how they work. And so what you'll see here is that the particle is coming in from bottom to top. And so it's moving up. It's that small red dot that's about to appear right there. And it's crossing a couple of laser beams, the purple lines that you see here. And so that's the particle coming in. It's scattering light from these lasers. That tells the instrument there's something there to analyze. It's done twice because in addition to getting a geometric size, how much scattering is done, you measure the distance between those two lasers, and that flight time gives you an aerodynamic diameter. Geometric diameter, aerodynamic diameter, combining those, you can also extract density from the particle. And so that's an important parameter that we get sort of free information. What's happening right now is that particle is being struck by a second type of laser, an excimer laser, that ablates the particle. It creates ions, and then those ions are extracted, and you'll see the positives going one way, negatives going the other way. You'll see that the lighter ions end up with the highest speed, and so you end up with a mass spectrum as a result, both positive and negative from the same particle. Essentially a complete chemical fingerprint from a single particle. So this is really the key to that challenge we sort of laid down in the introductory section. So for the engineers in the audience, again, just in case you want to geek out, this was a really fun instrument to design and build. In addition to being able to do this in SolidWorks to basically design the instrument before it was constructed, new techniques, things like 3D printing, metal work that we couldn't have even imagined back in the 1990s could be used on this. So you'll see the source region where these particles are ablated and ionized in the upper left. The white and the black pieces in here are 3D printed. There was really no way to machine them cleanly. On the lower right is the mass spectrometer, which you saw sort of in the animation in the last slide. This was designed initially using sim ion, so basically doing simulations of the ion path to increase the resolution and the sensitivity of the instrument as a result before even creating this. And this was work done by Dan Murphy out at NOAA. So again, I'll just show this very cartoony slide from Nicole's work again, just to say that this is an instrument that really gives us the ability to solve this problem, because you can take each of these particles coming into the instrument, essentially define the quantities that are shown here one at a time. And so then you can extract that information that we need to know to understand the atmospheric chemistry implications, the climate implications of these particles. And so sort of the Cliff Notes version to the second part of this talk is that I hope I've convinced you that this technique, single particle mass spectrometry, can be used to solve problems, starting with comets in the 1980s, but now to climate change in the 2020s. Okay, so how about our two case studies? Let's jump forward and start talking a little bit more about what we're finding out nowadays. We are going to have to reflect back to give us a little bit of context in a moment. So this first one that we're going to talk about is, I'll just title it What Goes Up right now, and you can probably guess how this is going to end. We'll start with our slide from that advanced placement textbook. And I'll just note that again, this is really fun and there's a lot of information here. And one of the things that you'll see are these meteors burning up in the mesosphere. And in fact, that is exactly what happens in the Earth's atmospheres. If you go out on a dark night, especially away from city lights, and you look up long enough, you'll see shooting stars. And these are meteors burning up at about 100 kilometers in our mesosphere. And I mentioned earlier that when Dan Murphy first flew this PALMS instrument into the stratosphere, one of the things that he observed, or one of the primary components that he observed, was this sulfuric acid in water, which had been understood for a long time to be the predominant thing in our stratosphere, the predominant aerosol type in our stratosphere. But what was interesting was about half the time he returned a mass spectrum that looks like the top panel here. And you'll notice that you simply don't see many ions from sulfuric acid in this one. Instead, you see these much more refractory components: iron, magnesium, aluminum, calcium, and so on. And so there's probably a few folks in the audience sort of screaming to themselves that you know what this is. And the fact that I just said that there was these meteorites burning up in the atmosphere and that you see these components now should give you a hint that indeed what this is meteoritic material, which essentially ablated, burned up in the mesosphere, and then fell down into the stratosphere. Now, on its way into the stratosphere, it does pick up sulfuric acid and water. It acts as a condensation source for sulfuric acid and water. So it becomes encapsulated in sulfuric acid and water. So again, the majority of the material in the stratospheric aerosol is sulfuric acid and water, but about 50% of it has a core particle, or core material, I should say, that comes from meteoritic material. Now, some of that meteoritic material is in solution and some of it remains apart. It's going to be a heterogeneous inclusion in it. We actually had to do quite a bit of work to prove this is the case. I had a chance to do my postdoc with Dan in the early 2000s. And so one of the first things that we did was we wanted to prove to the community that indeed these stratospheric flight spectra were meteoritic material, that they weren't something like mineral dust that had somehow made it into the stratosphere. And so we, to do this, we actually got meteorite samples, these from the Field Museum in Chicago. We were able to grind them up and dissolve them in sulfuric acid. And we had to show that the chemical fingerprinting was identical between these two things. We also built what we called artificial meteorite solution, basically putting the components that we knew from chondritic abundances into sulfuric acid and water to calibrate how much was there and make sure that we had the ratios and the chemical fingerprinting right. And luckily what you can see from these is the three things lie essentially right on top of each other. And you don't get that from just a random mineral dust from the surface, especially not when 50% of particles contain these. So after that time, I think the field really sort of took off for a period of years. Folks showed this process of particles ablating, or of meteors ablating in the mesosphere, this so-called smoke, meteoritic smoke, falling out and then acting as a condensation site for sulfuric acid and water on its way down. So what I want to get across is that the stratosphere is not simple aqueous sulfate particles. That is the majority of the material there, but it's not just that material. About half have metals in them from meteoritic material. And this can have implications on chemistry and cloud formation. But it's even more complicated than that. So I hate to tell you, but this is why I'm one of the things that I'm here today for. So indeed, we can use this new PALMS instrument and go back into the stratosphere and replicate that late 1990s result. So here is a beautiful set of spectra. You're seeing positives on the top and negative ions on the bottom of a meteoritic material particle that, again, is existing within this shell of sulfuric acid and water. So in the positive, you see that iron, magnesium, calcium, and so on. In the negative, you see the sulfate ions. What's quite interesting, though, is in the 2020s, if you do this, now about 10% of particles also have the components that you see in the bottom spectra. Again, third down is the positive of this particle, fourth down is the negative of this particle. We've eliminated the callouts to the meteoritic components in the top, so we're not repeating any of those things, but what you'll see instead is the material that now shows up in this particle that wasn't there in the top one. Aluminum, aluminum oxide, lithium. Again, I can probably hear people screaming out to themselves that they know what's going on here. And indeed, what this is a bit of material, not just from meteors, but now from spacecraft. So spacecraft ablation has been occurring in the atmosphere, spacecraft, anthropogenic spacecraft, that is, since the late 1950s, but it wasn't of a high enough scale to be detected or attributed until the 2020s. The materials that are noted here are rare in meteors, but they're common in launch vehicles. So the structure of a launch vehicle is largely aluminum alloys, light-weighted by lithium, and so that's where those two components come from. Things like niobium and hafnium are found very often in rocket nozzles, and so that's what you're starting to see here. But unambiguously not from meteors. It's just not of high enough abundance, nor was it detected in the late 1990s in anywhere near the quantities that are seen now. Meteors still dominate the mass that burns up in the mesosphere. Again, I said by particle number, you can sort of think 10% have the spacecraft material. But if projections hold, especially if some of the big constellations, Starlink, Kuiper, and some of these are put up, the mass coming back into the atmosphere from anthropogenic sources may rival the natural flux of meteors as soon as by the 2050s. The question of what impact this is going to have of adding these unique materials to PMC, PMC, by the way, are polar mesosphere clouds, PSC, polar stratospheric clouds, and cirrus is completely unknown. It's a new particle type, a refractory material that may very well be good at cloud formation. And then moreover, can these particles themselves promote some type of heterogeneous chemistry that leads to ozone loss is a completely unanswered question at this point in time. So just a quick slide, and this is from the paper that we authored with Dan Murphy's group now a couple of years ago, was again this idea that we are adding material, anthropogenically adding material, but not in the way that we sort of tend to think about that. It's not a surface source, it's a top of atmosphere source. So now this material is coming down, still acting as a condensation site, mixing with meteoritic material on its way down, creating these extremely complex particles that now exist and are quite common in our stratosphere. Okay, so as you probably guessed, the end result of what goes up is really must come down. So this idea that we burn material up in the upper atmosphere and it just goes away is not true. It really is being detected really as we speak in our stratosphere. And so that material is important. Okay. So I'm just looking at the clock and I see we've got about 15, maybe 20 minutes left. We're going to go on to the second of our sort of fun topics, second recent study, and we're going to just call this the summer of 2023. So I suspect this is a picture from Chicago, just north of us here. I'm sure that you all have pictures similar. I know that this was even a worse summer in places like New York City, but this was the Canadian Wildfire Center summer a couple years ago. Incredible aerosol optical depths. These really incredible sunsets took place that summer. We were over air quality alert standards in many of the northeastern cities as a result. And again, this was wildfires in Canada with that air advecting and then basically just sitting over the northeastern US. So we were very fortunate in that we had a chance to do some flights this year, and I'll talk about those in just a few minutes. But I did want to point out why I would be talking about this, because this seems like it would be a tropospheric phenomenon and not one that we would talk about in sort of an upper tropospheric, lower stratospheric sense. But what we have to remember is that there are ways to cross the troposphere. There are ways to put material from the troposphere into the stratosphere. Again, sort of belying this sort of simplistic cartoon that we had for the stratosphere early on. So this is from UCAR, a cartoony diagram of our lower two layers of the atmosphere. The green line here is meant to represent the tropopause, that delineation. And you can see things like, transport across the tropopause, especially in the tropics, gravity waves, stratospheric intrusions. But I want to call your attention to is what's happening in sort of the lower right here, which is this powerful convective storm somewhere in the mid latitudes, which is punching up not to the tropopause, but actually past the tropopause in this image. And so that's what we would commonly call an overshooting top. So a mechanism whereby we exchange air with the troposphere and stratosphere between those two. And not just air, but the gases in it, but also the particles in it. And so this was really the target of one of the NASA EV experiments or missions a few years ago. This was called DCOTS. This is Dynamics and Chemistry of the Summer Stratosphere, led by Ken Bowman down at Texas A&M University. And it was really targeted on this idea of overshooting tops. You can see one in the background here, beautiful example, and what material was being brought up as well as material was entrained and then brought back down. Okay. So this is going to be a busy slot with a few animations. I'm going to take a few minutes to explain this because I think it's really quite fun and also very important. So we were based out of Salina, Kansas. That's the red star here. That was done because a lot of these convective storms are happening in the Midwest U.S. Sort of this is the North American monsoon, as we would call it. And so that base gave us operational area over a lot of where these storms were occurring. So the aircraft would fly out. It would target recent convection and try to fly through that when it occurred in the stratosphere. So what you see here are sort of four different color codes. The light color is active convection. We're going to throw that out because that means that there was actually some kind of still overshooting top cloud material, ice crystals that were there. And that leads to a lot of artifacts. Recent convection means that overshooting had been there, but it had gone about 6 hours to about a day and a half earlier. Aged in this case means that there was some convective activity that took place, but it was about a day and a half to 5 days old. The white color is local background, meaning there was no convective signature for that area for at least 5 days. And then you'll notice some dotted lines here not considered. This is either when the instrument is calibrating or maybe we dipped back down into the troposphere. So we're gonna consider that active convection, that recent convection, that age convection, and that local background. And not surprisingly, the first two things we're going to look at are the sulfate particles and those meteoritic material particles, the ones that were observed back into the 1990s. Now, the caveat here is those meteoritic particles now contain about 10% of them contain some spacecraft signature in them as well. So that takes place and that was observed. But what's quite interesting, again, because we're considering the lower stratosphere now, is that there are a couple other important particle types that were observed. We're going to call this one carbonaceous sulfate. And this is going to be a combination of that biomass burning. Again, think back to those wildfires that are occurring, as well as organic. And so think in this case of those products that are being put into the atmosphere and then condensing from plants or from anthropogenic activities. And then this is an interesting one, a new category type, something that we had essentially never seen before, which is meteoritic material and biomass burning. And I'm going to just let that point rest for a second because this means a particle that coagulated in the stratosphere that has both a meteoritic signature, something that came from the mesosphere, as well as biomass burning, which came from the surface, met and coagulated in the stratosphere. So we can, in pie graph sort of world, think about what this looked like. So now, mind you, again, this is the lower stratosphere, the lower 4 kilometers of the stratosphere. And what you can see here is that something like 2/3 or more of particles are coming from a category which was this sulfate material or biomass, this organic material, there's biomass burning material, stuff that unambiguously had a source in the troposphere. It wasn't until we looked at the local background, we got away from this convective activity, then we started to see substantial amounts of that sulfate material, the classic stratospheric material, or this meteoritic material, again, a classic stratospheric particle. But even away from convection, there was still about half of particles had some influence from the troposphere, just showing how sort of polluted the lower stratosphere was during this summer. Now, albeit in areas that had convective activity frequently occurring. So to really illustrate this point, and now this is an image of a pyrocumulus system where a fire, a massive fire actually injects material directly into the stratosphere. This was an image from the Australian wildfire season from a couple of years before. But this is an image of again, that smoke cloud actually penetrating. You can see the thunderstorm just to the left of the number 4 here, where this overshooting top actually makes it into the stratosphere. But this is the idea of what's really going on, that we have a convective system that's powerful enough to entrain tropospheric particles and punch them up into the stratosphere. And again, just hammering home this point that more and more area is being burned as the climate warms. So I'm going to just show this in a vertical profile sense, just to give you some sense of what a big change we're talking about. Okay, so what am I doing here? I'm not using potential temperature anymore. Please excuse me for doing this. I'm going to do this relative to the local tropopause, just for clarity. So 0 says we're right at the tropopause, or as close as we think we can be. As we move above, that data is going to be stratospheric, or what we think is stratospheric data. Below is going to be tropospheric data. There's 4 lines here: pre-Ave, WAM, and crystal face. And then the 4th one is DCOTS, the mission we're talking about. Pre-Ave and WAM are historic PALMS data sets in sort of an unperturbed stratospheric sense. No deep convection taking place in the area, should be a very pristine stratosphere. And in fact, what you see here is what you would expect. You get to the troposphere, there's very little pure sulfate particle, and then you sort of break the slope, you get into the stratosphere, and you start seeing sulfate, this pristine sulfate particles come in. What's interesting is you go to crystal face, where there was a bit of convective activity, and that break doesn't happen until you get about 1.5 kilometers, 2 kilometers into the stratosphere. So again, these are previous PALMS flights. You go into the stratosphere and you don't start seeing pristine sulfate until you get well into the stratosphere. DCOTS is even worse. It was an even more perturbed stratosphere. And now in this case, you see that breakpoint isn't really happening until you get about 3.5, 4 kilometers into the stratosphere. We can show this likewise for the meteoritic material. So again, these pristine stratospheric cases, pre-Ave and WAM, PALMS goes up, hits the stratosphere, and the kink starts to break, the line starts to break over, and you start seeing meteoritic material as soon as you penetrate the tropopause or pass the tropopause. Crystal face, you don't see that until about 1.5 kilometers of depth. DCOTS, not until about 4 kilometers of depth. So it really highlights this idea that when you have convective activity, you no longer have that pristine stratosphere, that stratosphere that has these pristine sulfuric acid, maybe a bit of meteoritic material particles in it. And then finally, when we consider some of these carbonaceous sulfate particles, these organic particles, biomass burning and organics, the opposite is true. So again, this is the majority of particles in the troposphere, in the upper troposphere. But in this case, that material has been basically lifted 4 kilometers into the stratosphere. So the take-home message here is that this UTLS region, the upper troposphere, lower stratosphere, is really being perturbed by human activities, both from a top-down and a bottom-up source. And what's more interesting than that is that these particles are starting to mix there. So we're already starting to see coagulated particles that have a signature both of meteoritic material and spacecraft particles, as well as biomass burning. The same particle is a combination of both from coagulation. Okay, so just checking my clock here with my final 5 minutes or so, I'd like to go on to some future work. So this is sort of the world according to Dan, what I see as the next steps here. So probably a lot of folks in this in the seminar are aware of the ATOM mission, which occurred many, many years ago now. This is a great mission led by a number of different groups, Steve Wofsy out of Harvard, as well as others. And the idea here was to basically do vertical profiles through the troposphere up to the tropopause. This was done with NASA's DC-8, and do it in a pole-to-pole sense in different seasons and in different longitudes. And so you can see that idea here. These are basically flight paths. DC-8 goes up, measures, stops, goes back down, and this is sort of a max altitude of the DC-8 event. So what I'm going to propose is I think that we need to do this, but we don't need to essentially start at the surface. That's been done by ATOM. We really need to be thinking about starting in the UT and penetrating as far as we can into the lower stratosphere. So this would probably have to be done by something like NASA's ER2 or NASA's WB-57 instead of the DC-8. And again, do this basically through as deep as you can penetrate into the stratosphere from pole to pole, as far as you can get north, as far as you can get south, and do this in presumably different seasons, because we know the dynamics of the stratosphere switch over into the wintertime pole. And so that's the type of thing that we really need to do to understand these phenomena that are going on right now. Another thing that we need to do is really in the laboratory. And so what you see here are some pie graphs, and I'm going to apologize because in typical Excel format, it always color codes the biggest thing with one color. So the compositions are changing here. But we're just starting to get an understanding of what meteoritic material can do to affect cloud formation and climate. But now we're starting to put completely different material in from spacecraft. And so we really need to redo those studies or really expand all of these studies to understand what this new material, the spacecraft material, what impact that's having. And I'll just point out that we have really very little of data about this. This is a paper that came out of Mario Molina's group. This is back in the late 1990s. They considered one of these ozone important reactions on aluminum oxide. The reason they chose aluminum oxide was that at that time, space shuttle was being launched. And this was one of the things that came out of burning the solid rocket motors was this aluminum oxide. So they considered how this might promote heterogeneous chemistry important to ozone depletion on this material. But we know that now that that's not the state of this material in the atmosphere. Instead, it's these small metal inclusions in sulfuric acid and water, as well as that material being in solution. And so a particle type that looks more like this, or a solution that looks more like this, is really what we need to be doing those experiments on now. So forget about the pristine aluminum oxide. Think more about sulfuric acid, water mixtures with material in solution, as well as inclusions in it. That's what we need to be doing. And we're starting to do some of this in collaboration with JPL. We're starting to do some of the solubility studies. What amount of this material is in solution? What can you think of as being in the aqueous phase? And then these inclusions here, what amount of material? So something like iron is quite interesting because it's very likely that some of it is in solution, but some of it also remains insoluble. It's above its solubility limit, and so it remains as an inclusion in that particle. And then finally, something that I'm sure a number of folks have thought about here is that, I'm sure you're aware that there's these proposals to put particles into the stratosphere, to use them in some type of an albedo modification sense to try to essentially reflect additional radiation back into space to cool the surface. Well, as far as I know, those thoughts really exist in an atmosphere where the stratosphere is pristine sulfuric acid and water. Very few of those studies actually consider that there's meteoritic material there. I don't know, you guys can tell me, I'm not aware of any studies that consider spacecraft materials there or biomass burning materials there or other tropospheric particles that can be lifted by deep convection there. And so this much more complicated stratosphere is the one that we have to think about being impacted by ideas for geoengineering, for albedo modification studies in the future. Okay. So I think my time is basically up. I'm trying to keep an eye on the clock here, and I think we're right on time. So I'll just give you a few closing thoughts. If we're going to consider intentional changes to the upper troposphere and lower stratosphere, these albedo modification thoughts, we really have to know what we're doing to unintentionally change it. What are we putting there, maybe from increased biomass burning at the surface or increased spacecraft ablation? It's not only that, it's not only what does that world look like in 2026, it's really how is it going to change? If we really do bring online Starlink or Kuiper and we have 10 times or 50 times as many satellites burning up every year, what is that stratosphere going to look like? If we're burning twice as much or 4 times as much surface area every year, what is that stratosphere going to look like? And I think that really means developing tools that are not only for use in the field, maybe one of these tomography type missions, but also in the laboratory and also from a modeling sense. How do we model that stratosphere correctly? So with that, I'd just like to say thank you all for your time. It's a real pleasure being here again. I'll just reiterate that, looking at who you've had give these seminars in the past, it's really just a pleasure to join you. So with that, I'll turn it over to Kazi, and I'm happy to take any questions you might have.
Well, thanks, Dan. That was great. So now we can open up for questions. So if you want to ask a question, go ahead, Russ. He's already at it. So you guys can all raise your hand or post your question in the chat. But Russ can start us off.
Hey, good afternoon. Great stuff. Russ Dickerson, Atmospheric and Oceanic Science. Um, I guess it's more of a comment that the upper trope, lower strat, being the coldest part of the atmosphere, is plays a critical role in the radiative balance. So anything you do that can change the heating in that part, adding dark aerosols or uh, species that absorb infrared radiation will have a profound impact on circulation. I don't know if you mentioned that or not, but I think it adds urgency to the understanding. Then there, and if you can comment on my comment, then I have a really quick follow-up.
No, I'll just 100% agree with your comment, and I didn't have time to mention it, but absolutely, if you put a dark absorbing particle at that level, boy, that could have some huge impacts. And I know this is being considered with albedo modification, but now you're talking about biomass burning, and then changing the optical properties of what we used to think of as being sulfuric acid and water. So you're 100% right.
Right. And oh, decades ago, we actually flew through thunderstorms in the far north over North Dakota and noticed that overshooting tops were frequent and that the boundary layer air can get into the lower stratosphere frequently and has a profound impact. So just garden variety pollution can contaminate the upper trope, lower strat. So we have to uh, keep the pressure on to not let the boundary layer of the planet get any worse.
No, I think you're 100% right on both counts. And it is interesting because I think there is a lot of old studies that really sort of emphasize this point. Now, 2022, 2023, when we were looking at some of this, I think it probably was highlighted by the amount of biomass burning that we're now seeing,
Right.
coincident or even before what we sort of think of as being the most active convection season. And so that timing is something that I think is starting to play into it as well. So, but certainly even just with the data from Palms going back into the early 2000s, reanalyzing that data, we can even see that signature was there.
Yeah, I can tell you in the late 90s, the community was not prepared to believe that the tropopause is anything other than an iron lid. So glad to see it's mainstream now.
Yeah, no, I'm sure this would have been probably thrown out in that time period, but luckily we got some traction on it now.
Excellent.
Thank you.
Thanks, Russ. Next is Mark.
Okay, thanks. Uh, let's see. Sorry. Dan, thanks very much for that great talk. I was actually at Caltech in the 80s doing some single particle experiments. Not quite what you guys are doing, but it had some bearing. My question to you is, what are your thoughts on the internal mixing of a given particle, even if you have a wide variety of ions? They're not, you know, for example, with a biomass burning and sulfuric acid particle, where is the organic stuff? Is it in the core? Is it on the surface? And how well can these particles mix? Like, if the sulfuric acid and water is frozen, it's not going to be sort of like a normal liquid aqueous solution like we might think. Anyways, the whole point of this being that the surface is largely going to determine what might happen from a cloud generation point of view. And so what's on the surface of the particles?
Yeah, that's really cool, Mark. But by the way, I think the PI that I was thinking of was Sinha, was his name. I don't know that I ever had a chance to meet him, but yeah, there was some really neat work going on in this in Caltech, and it was just lucky to have technology sort of finally catch up with these ideas. So I think you raise a really interesting question, and there's others that are probably more capable of answering this. I'm sort of thinking of like Alan Bertram's group that does this sort of core shell partitioning work. And it gets very complicated very quickly. So you mentioned organics and sulfates. And I think what they've shown is that depending on what the organic is, it can end up at the surface, it can end up in the core, or it can form essentially like islands on the surface. And so then the atmosphere has access to both the sulfates and the organics, not one or the other. But it's very much sort of a component, or whatever that organic is that dictates that. Um, You alluded to the fact too, when ice forms, and there's this idea that, when ice forms, you actually push sort of like the salts or whatever out to the surface. You form these like quasi brine pockets on the surface. And so that's another aspect of this, is that, you're probably not just forming ice and then you don't have a pristine ice layer on the surface. You actually have part of the particle, maybe in a more concentrated form, forced to the surface as well. And then these meteoritic ones, I'll just point out, are even more complicated than that, in that, you have metal ions in solution, changing the solution itself. It's no longer sulfuric acid and water pure. It has metal ions in solution. And then you have inclusions in it. And so you can imagine all the crazy different combinations of heterogeneous chemistry that you can get off of that. Again, I think there's probably as many different models and surfaces as we could all think up, in the remaining time here, and then some. But I do think, I just want to give a shout out. Like, I think Alan's group has done some really nice work looking at this kind of thing. What's on the core, what's in the shell, when does it not partition, perfectly like that? Yeah, that's fascinating work, and it's very complicated. So sorry, that's probably not a complete answer, but that's kind of where the field is.
Thanks.
Thanks, Mark. Next is Ross.
Okay, thanks for a great talk. Appreciate you taking the time to speak with us. So I was going to ask you about geoengineering until I saw your second last slide. So I'll skip that and go to your notion of a mission using either ER2 or B57, which I certainly agree with. Have you thought about what payload you would fly? I can make it easy and say, starting with DCOTS, would you take anything off or add anything? As we both know, the DCOTS payload was jam-packed. But regardless, what in addition to Palm's next generation do you think is essential to be on a payload like this?
Yeah, so Ross, that's a great question. I think you know this area better than anybody, and so I should probably be asking you, what should we put on it? I think you probably answered the way that I would, which is, I think you start with the DCOTS payload, and just for the group here, this was a very particle centric talk because that's what our group does, and I apologize for that. The gas phase measurements are critically important. So I think that part of it, certainly, the tracers, the standard package, that has to go on here. In that sense, yeah, I think you do. You start with the DCOTS payload, and you kind of go from there. I mean, in my opinion, that's probably one of the more comprehensive payloads. The B57 payloads that are being talked about, the next campaign. I think they're calling it Sabre. That has the other Palms NG instrument, the one that lives at NOAA, is on board that one. The DCOTS and the Sabre payloads have a lot of similarities. It's kind of, yeah, very, very, very similar instruments, even if different PIs, different capabilities. But I think that's where you sort of start.
Great. And can I ask a follow-up, Cassie?
Yeah, I don't have anyone behind you in the queue, so go ahead.
Super. That's what I was getting at there. Great. Have you also thought about how either the 57 or ER2 could actually do this? Because I'm going back in my mind to Adrian Tuck back in the day wanting to do this. And my memory was that it had to be east-west, that north-south over ocean really wasn't feasible given the characteristics of both the 57 and the ER2. But have you thought about how you would actually pull this off logistically?
Yeah, a little bit. And, certainly this is something that I'd love to talk with you sort of offline about, but it's probably good for this audience to know a couple things. One is that, our stratospheric capabilities, planet-wide, if you want to put it that way, are extremely limited. We really just talked about the two aircraft that can do this. You get a few things like G5 that can touch on the lower stratosphere as you go north. But it's really ER2 and B57, and even the Russian asset, the Geophysica, is essentially no longer available for scientific work. ER2 is important because B57 has fairly limited range. You're talking about maybe 5 hours. And so, you need ER2 to get anywhere reasonably close to either pole. And so you've got that aircraft. Even doing that, I think to Adrian's point, where can you fly? Like, you can't do these long legs over water with either aircraft in a way that DC-8 could do, where you had a much, much longer range. And so you almost are forced to sort of like go down, North and South America. That's the kind of thing that I think Adrian was getting at, that you'd have to do. But something's better than nothing. And I think that's what we probably need to be thinking about as a community. So both of those things, right? What are our next assets that can actually do in situ measurements in this part of the atmosphere? Because ER2 and WB57 are not going to be around forever. Dan Murphy was just saying the other day that they're 60-year-old aircraft, basically 60-year-old designs at least. How are we going to do this, especially if we start thinking about that we want to do something to our stratosphere, which I think is very premature at this point. But nonetheless, if we're starting to talk about that, we have no monitoring capabilities, and we very likely will have less in the coming years.
NCAR's G5?
So G5 has about a 50,000 foot max altitude. B57 is 65, ER2 is 70. And so, G5, you can get into the stratosphere in sort of the northern latitudes, but you can't get there in the mid latitudes, certainly not the tropics.
True.
So yeah, it's a tough one.
Dan, I'll be delighted to follow up with you on this. Thank you.
Thanks, Frost. Do we have any other questions while we still have Dan here?
Well, shoot, then I'll just take a quick second to say thank you again. This was really fun, and I really appreciated the questions too. This was great.
Yeah, thank you so much, Dan, for giving us this talk, and thank you everyone for joining us for another seminar. Just a reminder, we will not have one next Monday, or this Monday, I guess, because of UMD spring break. So have a good break. We will see you all in 2 weeks. Thank you.